Hello, welcome back to Algebra. The title of this lesson is Zero and Negative Exponents Part 1. Now, I get excited about teaching certain lessons, and this is one of them actually, because I remember when I first learned the concept of an exponent. Something raised to the zero power didn't make sense. Something raised to the -1 exponent to me at the time didn't make a lot of sense, because I can visualize 3 to the power of 2, 3 times 3 is 9. But I can't visualize 3 to the 0 power. That doesn't make sense. And I also can't visualize very easily 3 to the -5 power. So what we're going to do in this lesson is we're going to talk about these rules that involve zero, exponents that are zero, and exponents that are negative. And I'm going to write those rules down, and we're going to talk about them, and I'm going to actually show you where those rules come from. Because when I first learned algebra, nobody told me where they come from. I just had to learn them, right? And it's just one of those rules you have to learn, you have to memorize, but you don't have any idea what it means. We're going to talk about what it means and where it comes from here, and then at the end we're going to do several problems to give you practice with zero and negative exponents, and then we'll have more complicated problems in the next lesson. So before we get too far into this, let's write down the two rules that we have for zero, or at least the two basic rules for zero, exponents that are zero, and exponents that are -1. And those go as follows. Any value of a variable number, whatever, a, raised to the power of 0 is always, 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 always equal to 1. So if you see an equation later on down the road in calculus, trigonometry, algebra, anything, if there's a term raised to the 0 power, you just say it's 1. You don't have to think about it. You don't have to manipulate it or show it. It's just a fact. It's something that we take to be true in math that you don't have to prove every single time you use it. And I'm going to show you why in a minute, but this is a rule that you're just going to end up having to use all the time. And then we also have another rule. Let me tell you one important thing. When we say that a to the 0 power is 1, we are implying that the variable a cannot be equal to 0 because 0 to the 0 power is undefined. So I should have said that before. So when I say a to the 0 is 1, what we're really saying is, 1 to the 0 is 1, 16 to the 0 is 1, 32 to the 0 is 1, -5 to the 0 is 1, -64 to the 0 is 1. All that's true, but 0 raised to the power of 0 is not defined. And you'll see a little bit more why as we go through the derivation why it's not defined, but you can't have an equation with 0 raised to the 0 power. Now the other rule that we have involving exponents like this is a base raised to a negative exponent can always be written as follows. Just take that exponent, the base and the exponent, and move it to the denominator of a fraction and make the exponent positive. What this is saying is that if I have a negative exponent up here, just to take a concrete example, for instance, if I have 3 to the -6 power, what it means is it's exactly the same thing as putting it in the denominator of a fraction with a positive version of the same exponent. These are by definition equivalent. So here I've written it with the number 3, but it applies to any variable. So x to the -n or y to the -n, whatever, or x to the -6, x to the -5, whatever. You just put it on the bottom and make the exponent positive. These are equivalent. So these are what we call the important rules of exponents. Well, there's lots of rules of exponents, but these are the rules that involve zero and negative exponents. And again, as I said, when I first learned these rules, someone said, hey, these are the rules, you have to use them. But I didn't understand where they come from. So I want to take a minute to show you where they come from, and then we will do some problems showing you how to simplify expressions that involve negative exponents, because I know you may not believe me now, but you'll have to trust me, negative exponents will be in your life forever. They're used all throughout calculus, physics, chemistry, everywhere. Equations with zero exponents, equations with negative exponents are everywhere, so you're just going to have to get used to it. So let me start out by a concrete example. Let's take any number, doesn't matter, because here I'm using a base of a. That's what you'll see in your book. Let's bring it down to earth and say we have a number, 4 to the 0 power. Now I know that I just told you anything to the 0 is 1, and it is, but let's just hold that in the back of our mind for a second. So we know we can have a 0 exponent. We also know we can have the positive exponents that go up like this, 4 to the power of 1, 4 to the power of 2, 4 to the power of 3, 4 to the power of 4. So here we start 4 to the 0. We can increase the exponents here, right? And now we haven't talked about these yet, but now we know that also on the left-hand side we have negative exponents because these are the positive numbers, these are the negative numbers, so we can have negative exponents. So here you might have 4 to the -1, 4 to the -2, 4 to the -3, 4 to the -4. right? Now, I just told you a minute ago that anything to the 0 power is 1. But first, let's just hold that in our back pocket. Let's go all the way to the end. When you write this, actually, let me back up for a second. Let's write it like this. Let's write these over here. 4 to the 0, 4 to the 1, 4 to the 2, 4 to the 3, 4 to the 4. According to this rule here, this one, which I haven't used yet. Let me erase this one. According to this rule here that I haven't used yet, but we're going to use it for the first time, 4 to the 0 power is 1. And according to this rule, which we haven't used yet, but we'll use it now, this guy is really equal to 1 over 4 to the first power. And this guy is really 1 over 4 to the second power. And this guy is 1 over 4 to the third power. And this guy is 1 over 4 to the fourth power. So you see how the pattern goes. You have exponents that are whole numbers, and then again, the exponents are whole numbers here, but they're in the bottom of the fractions. So why am I doing this, you say? Because as you can see, let's start off on the right-hand side. What is 4 to the fourth power? That's 4 times 4 times 4 times 4, right? Which means that this is going to be 256. You can verify that in a calculator. 4 times 4 times 4 is 4 to the third. That's 64. 4 squared, you all know, is 16. 4 to the first, you all know, is 4. Then we have this number 1, which lives in the middle. Now, if 4 to the first is 4, then 1 over 4 to the first is 1/4. That's what's this here. And if 4 squared is 16, then 1 over 4 squared is 1 over 16. And by similarity, this is 1 over 64. And this is 1 over 256. Why am I writing all this stuff out for you? It's because I want you to see that kind of in the middle here, we have the 0 power. That's the middle here, which means that it evaluates to 1. I haven't proved it to you yet, but anything to the 0 is 1. As you take your base and have positive exponents getting larger and larger, the value of the thing you have is getting bigger and bigger because the exponent's getting bigger. It makes sense. But then as you start from your neutral point again and go the other directions, the numbers get smaller and smaller because 1/4 is bigger than 1/16, is bigger than 1/64, and is bigger than 1/256. These are really small numbers, and these are larger fractions, and then these are even larger whole numbers. So really what you have is, you have smaller going to bigger. Why am I doing all this? I want you to get in the back of your mind that when you have negative exponents, it means that it lives in the bottom of the fraction, which means the value of whatever it is a small number, right? When you have 15 to the negative 20 power, that's a small number, not a big number. A lot of people think, oh, the 20 power is huge, but the negative means it's in the bottom of a fraction. So just like this guy was in the bottom of a fraction, it means this is really, really small. This is a small decimal. This is also a decimal, 0.25, but it's much bigger. Then we have 1, which is neutral in the middle, and then it gets larger from there. So the negative exponents, when you get negative large exponents, negatively, you have really, really small numbers, increasing as you get to the 0 power, which is the neutral point 1, increasing even more, getting larger. So the whole scale of it is smaller to bigger. Frequently in science, we'll talk about it later, scientific notation. You know, atoms might be 10 to the minus 10 meters. The minus 10 meters. That means a really small number. Whereas galaxies might be really far away, 10 to the 20, whatever unit it is. So negative exponents means small numbers, positive exponents mean large numbers. So I want you to get that in your head. Now I want to turn my attention next to showing you why this is true. Why is it that anything to the 0 power is 1? Of course, except 0 raised to the 0 power, that's undefined. And why is it that anything raised to a negative exponent is just a fraction with the exponent turned positive and brought into the denominator? I want to go over why those rules actually work. So let's take them one at a time. Let's talk about this first one first. So we'll say rule 1, which is what? A to the 0 is equal to 1. So let's start in math. When you do a proof like this, usually what you do is you start with something you know is true. And we know that a base to an mth exponent times a base to the nth exponent. These are different numbers. Like it could be a squared, a to the third. What do? If the bases are the same, the exponents are different, you add them, right? So it's a to the m plus n. This is exactly like a squared, a to the third. You add them. 2 plus 3 is 5. We add the exponents. But what if n was equal to 0? In other words, we're trying to show that what if an exponent is 0? Let's set one of these exponents equal to 0. and see what actually happens. Then in that case, what we would have on the left side here, we would have a to the m, but let's set n equal to 0. Then on the right-hand side, we have a to the m plus 0. So all we're saying is we know this is true. We've been using exponent addition forever. Let's set one of the exponents to 0. That means that it's going to be one of them set to 0 added up here. So what do we have in the next step? It'll be a to the m times a to the 0 equals, well, what happens when you add 0 to something? You're just going to get a to the m back again. Okay? Now we want to figure out and prove that this is equal to 1. So how do we isolate it? We're going to divide both sides by a to the 0 power. So you have a to the m, a to the m. What do? We took this equation, we divide by a to the m, that kills it on the left. Divide this by a to the m, and you can see that what you're going to have, this is the same on the top and the bottom, so they cancel, or you can think of them as dividing and always giving you 1. So we've proven that any variable raised to a 0 power is 1. Any number raised to the 0 power is 1. Now, if you go back to the original rule that we had, we said that this was true, but only if a was not 0. We said that 0 to the 0 is undefined. It doesn't exist. Now, from the proof, we can see why. Because if we allow a to actually be 0, so it's 0 to the 0 power, then that would mean you would have 0 to the m, 0 to the m, right? But on the bottom, cover up the top, 0 raised to any power. 0 raised to any power is going to give you 0. 0 squared is 0 because, 0 times 0, right? It gives you 0. 0 raised to any power gives you 0, right? So if I have a 0 in the denominator of this fraction, I can't divide by 0. I mean, in calculus, we say it approaches infinity or something, but in real life, you can't actually divide something by nothing. You get an undefined, nonsensical answer. So because we can't do that, we exclude the possibility when a is actually 0, and so we say 0 raised to the 0 is not defined because you have problems actually pulling this off. But for any other value of this variable a, when you raise it to the 0 power, you always get 1. All right? So that's where it comes from. Now let's talk about rule number 2. So rule 2 is almost more important, really. A to the negative n is equal to 1 over a to the n. This is the one you're going to use constantly when you're solving problems. When you see a negative exponent, you just make it a positive exponent by pulling it downstairs. Why is that true? It seems like magic, right? Well, let's go back and start with what we know. And we know we're going to start from exactly the same point as the other guy. A to the m, a to the n, we just add these exponents, m plus n, just like we did there, no difference. But now, let's say, what if one of these exponents, m, is actually equal to negative n. In other words, we want to set one equal to negative n, so we'll make one of these exponents equal to negative n. What's going to happen when we make that substitution? So if this is negative n, it'll be a to the negative n times a to the positive n equals a, what do you have here? Negative n plus n. All we did was make the substitution and put it in there. Now what's going to happen is when you add negative n to n, a to the n equals, what are you going to have? A to the n, negative n plus n is a to the 0. But you already know that a to the 0 is 1. So what you really have is a to the negative n times a to the n is equal to 1. So now we're trying to prove to ourselves what happens when you have a negative exponent. What you're going to have is divide both sides of this equation by a to the n, and you're going to get 1 over a to the n. Divide the left side by a to the n, canceling. Divide the right side by a to the n gives you this. That's the final answer. So these are the two rules that we set out to prove. And notice that all we did to get those rules is we start with exponent addition. We know that we have the same base, different exponents. We add the exponents. We started from the same place in both cases. This case, we said, let's let one of these exponents equal 0. In this case, we said, let's let one of these exponents equal a negative number. And then we just flow through it and we find out that when you raise anything to the 0 power, you always get 1. And here when you raise anything to the negative exponent, negative n, it's the same as the reciprocal of that positive exponent, 1 over a to the positive version of that same exponent. That's where they come from. Will you need to use these proofs in real life? No, probably, unless you become a mathematician. But we do need to use the results all the time, because in equations, very often you'll have an exponent or something raised to the 0 power. And even more common than that, we will have some expression raised to a negative exponent, which means you'll have to write it basically as a fraction to simplify anything. So now that we have all that underway, I would like to give you a few kind of easier problems. They're not super easy, but they're relatively baby step problems to get used to the idea of this. And then in the next lesson, we'll solve even more complicated problems. Let's do the first one on this board right here. What if we have, very simple, start kind of basic problem. What if we have 3 times 5 to the negative 1, right? We cannot add these exponents because we have different bases, right? But what we do know is that when you have a negative exponent, we write it as a fraction. So this is going to be 3 times. This is going to be written as, what did we say? 1 over the positive version of that exponent. 1 over the positive version of that exponent, which was negative 1, now becoming positive 1 once we move them downstairs. Then what do we have? If you want to be explicit, this 3 is really 3 over 1, and it's multiplied by a fraction 1/5, because 5 to the 1 is 5. You multiply the tops, 3 times 1 is 3, multiply the bottoms, and you get 3/5. All right, 3/5. And that's the answer. So when you see a negative exponent, you need to write it as a positive exponent in fractional form, deal with the fractions, and then get the answer. That's why I stress so much in the beginning of all of these algebra classes how critically important fractions are, because it comes into play all the time. All right, let's take another one, slightly more difficult. What if we have negative 3 to the negative 1 power raised to the negative 2 power? I think I'm going to solve this 2 ways, which I didn't actually do in my original in my notes here, but we're going to do it 2 ways because I think it's important for you to see that all of the rules work. The first way we're going to do is we're going to focus on the inside. We have negative 3 to the first power. Now this negative 1 exponent does not apply to the negative sign here because there's no parentheses around it. If I had the whole thing wrapped in parentheses, then it would apply, but when there's no parentheses, the 3 gets the negative 1 exponent. This negative just sits outside. So what you really have on the inside is negative 1 over 3 to the first power, which is 1/3, of course. All right? So what you have is, just to be 100% clear, you have negative 1/3 to the negative 2. All right? Now this entire thing has a negative exponent associated with it. So don't get scared by that. Okay, you got a fraction. It's raised to a negative exponent. Students are like, well, what do I do now? It's a fraction inside. It's the same rule. Whatever you have that's raised to a negative exponent gets moved to the bottom of a fraction, and you're just going to have to deal with the fact that sometimes your fractions are going to look ugly for a little while. But we'll do enough problems where they won't be too bad. What we have here is, what you'll have is, it'll be 1 over this quantity here, this entire quantity, negative 1/3, raised to the power of 2. See, I just took whatever had the negative 2 exponent, I moved it downstairs, and I made it a positive exponent. Everything in the middle remained the same. Now, on the top stays the same. On the bottom, what do we have? We have negative 1/3 squared, which means negative 1/3 times negative 1/3. Negative times negative is positive, and 1/3 squared is 1/3 times 1/3, which is 1/9. It's positive because the square applies to this negative, so negative times negative gives you positive, and this times this gives you 1/9. You square the top, you square the bottom, you get 1/9. Now students look at this often and have no idea what to do, but it's just division. It's something on the top divided by something on the bottom, which happens to be a fraction. So what you really have is the top here is really 1 over 1. The number 1 can be written as 1 over 1. Change it to multiplication and take the bottom, flip it over. That's how we divide fractions. We take the bottom, flip it over, make it multiplication. What do you get? 1 times 9 is 9. 1 times 1 is 1. And of course, you know 9 over 1 is 9. So the answer is just 9. A couple of things I want to point out before we go to the next problem. 1 over a fraction, I want you to do it like this, but in general, after a while, you'll start realizing when you have 1 over a fraction, it basically just means you take the reciprocal, and that's the answer. So the reciprocal of 1/9 is 9. I'm showing all the multiplication to make it clear what's happening. You're dividing something, you change it into multiplication, and that gives you 9. But when you start seeing lots of fractions on the denominators of larger fractions, you'll realize you can kind of flip them over because that's what's happening. We can kind of think of this 1/9 as being like a trapeze artist. He's kind of hanging. He can swing up and flip himself upside down to the top. That helps you. Whatever. Everybody does things differently. But that's what's going on here. This division becomes a multiplication. You flip it. Now, I do think it's very, very important for you to understand different ways of doing things. So I want to take this problem and do it again differently. Negative 3, and I don't even have this in my notes, so hopefully I don't fumble it too much. But I think it's important. What we have here, remember I told you a long time ago, what if we had, before we tackle this, let's go over here. What if you had x squared and it was raised to the 4th power? It's a power raised to a power, right? It would be x to the 8th because you multiply those powers. Just because this is a negative exponent doesn't mean that it has different rules. If you have an exponent raised to an exponent and one of those exponents, or even both of them, are negative, that's okay. You still multiply them just like you do with regular old exponents. It's just a negative exponent. So what this means here is that I'm going to have this -2. It's going to apply to everything inside. So the best way to do it is for you to realize that it's like this. -1, which is what's in front of here, this -1, is going to be raised to the -2 power. Okay? And then this guy here, 3 to the -1, is also going to be multiplied or raised to the -2 power. So this power gets applied to this number, which is -1, also to this, which is itself an exponent, which is kind of weird. Let's go down and proceed. What's going to happen here? -1 to the -2. What's going to happen is it'll be 1 over whatever this is, -1, and we make it positive, square. We take it, move it to the bottom, make it a positive exponent because that's what we do. We move them downstairs. That's going to be multiplied by. Now you can do it different ways. You can make this 1/3 and square it, but I want to show you different ways of doing things. You can say the -1 times -2 because it's a power raised to a power, just like this is. So -1 times -2 gives you what? +2. So 3 squared. All right? So what am I going to have? On the top, I'm going to have 3 squared, which is 9. On the bottom, I'm going to have -1 squared. What's -1 squared? It's +1. And the answer I get is 9, exactly as what I got before. So there's lots of ways you can do things. If you see it's an exponent raised to an exponent, you can multiply those exponents, even if they're negative exponents. The answer that you get is going to be the answer you get. Or you can start writing them as fractions and squaring them and manipulating them and multiplying them and all of that using the same rules of exponents that we've used in the past. If you're doing things correctly, you will always get the correct answer. Now, what if I have 2 to the -2 power times 3 to the -1 power times 5 to the 0 power raised to the -1 power. There's lots of ways to do it. Okay, I could take this negative exponent and apply it and multiply it times this exponent and apply it and multiply it times this exponent and apply it and multiply it times this exponent. That's fine. But in this case, I'm just going to work in the middle first. This becomes, let's open up a big parentheses here, 1 over 2 squared, moving it to the downstairs, making it a positive exponent, times this goes downstairs, making this 1 over 3 to the 1st power. But 5 to the 0, you always know, anything to the 0 is 1, so this is just 1. Now this entire thing is raised to the -1 power. All right, so what are you going to have here? You're going to have 1/4 times 1/3. You have times 1 there, so I don't need to write that, but it's -1. So let's multiply this fraction. 1/4 times 1/3, multiply the tops, multiply the bottoms. Again, it's to the -1 power. So I kind of hinted here that when you have to the -1 power, this is what you have here, 1/9 to the -1 power, basically. You can just basically flip it, and that's going to be the answer. But I think it's a little bit more clearer to show it here. What you're going to have here is, since it's -1 power, 1 over 1/12 to the +1 power, taking that negative exponent, moving it down. But that means that the numerator is just a number, 1 over 1, times, I'll change the fraction division to multiplication. I got to flip that bottom fraction over to do that. Whoops, this should be 1/12, sorry, like this. And so what you'll get on the top is 12, and on the bottom you get 1, which means you'll get 12. And so that's the answer. So again, go ahead and move it to the bottom, then that fraction division becomes multiplication, then you get the answer all in steps here. But also, in the back of your mind, when you have numbers raised to a -1 power, it ends up just flipping the thing over, giving you 12. I don't like teaching people to take shortcuts like that because you can get into trouble. What if it's 1/12 to the -3rd power? Then you might forget to do something. It's better to just move it down, keep the exponent, and do everything appropriately. But I am trying to teach you different ways of thinking about these problems. All right, we only have 2 more. One a little bit easier than the other. This one's not too bad. What if you have 2 multiplied by 2/5 raised to the -2 power? So again, many ways of doing it, but I'm going to do it like this. What if we kept the front here. This is raised to the negative 2 power, so I'm going to multiply that by 1 over the fraction 2/5. But that fraction is raised to the positive 2 power. I moved it downstairs, made it a positive guy here. Then it's going to be 2 times 1 over, this is a fraction raised to an exponent. The numerator is raised to the power of 2. The denominator is also raised to the power of 2. I know that you don't like the idea of having an ugly fraction like this in the denominator of a larger fraction, but you're going to have to get used to it because it's just like that in algebra. So let's keep the 2 times here. In the bottom, 2 squared is 4. 5 squared is 25. So there's a couple of ways to proceed, but basically let's keep the 2 out in front here. Now this is fraction division. It's a number divided by a fraction. So let's write this as 1 over 1 multiplied by, because that's what it is, 1 over 1. We'll take this, we'll flip it over and multiply, 25 over 4. So you see what's happened. You have 2 times this times this. So what you really have is 2 over 1 from this times 1 times 25 over 4. Now you multiply the numerators together, giving you 50. Multiply the denominators together, giving you 4. And then 50 over 4. You need to think of something to divide top and bottom by. 50 divided by 2 is 25. 4 divided by 2 is 2. So 25 over 2. Final answer. I can't divide top and bottom by anything common anymore. 25 over 2 is the final answer. There are several places through this that I could actually think right now off the top of my head to do it slightly differently, getting the same answer. This is the way I did it when I did it the first time. But just looking at it again, another way to go is, instead of rewriting this down below, you could take this fraction and you could distribute the negative 2 as an exponent to the top, and then the negative 2 as an exponent to the bottom. And then continue to simplify it that way. But then you would have 2 negative exponents, and it would be more fractions divided by more fractions, and you would get there. You would definitely get the right place, but it would be a slightly different path than the way we took it. Okay? Now, so far, all of these problems have had just numbers. I would like to, in this section, at least do one problem involving variables with negative exponents. So here we go. 3 times x to the negative 2 divided by y to the negative 1. Now, before learning about negative exponents, this looks terrifying to most people. It just looks ugly with the negative exponents here. But now I want you to take it one step at a time. We know that x is raised to the negative 2, so we write that as a fraction. I know it's ugly in the beginning. You don't want to do this stuff. But what you end up getting is 3 times, you move this into a fraction, 1 over x squared, making it positive. But this whole thing lives in the numerator of a larger fraction. So I draw a larger fraction line down here. And then the bottom, I make this a fraction, 1 over y to the first. I've turned this into a fraction. I've turned this into a fraction. I've preserved the structure of the original thing. Yes, it looks ugly. You're just going to have to get used to that. Now on the top, it's going to basically be 3 over 1 times this. So you multiply the tops, 3, multiply the bottoms, x squared, because you're taking 3 over 1 times this, multiply tops, multiply bottoms. On the bottom, you're still going to be stuck with the 1 over y. But then you have a fraction divided by a fraction. We know how to handle that. You take the top fraction, change this division here to multiplication, take the bottom fraction, flip it over, and then we can now finally multiply them. 3 times y will give you 3y, and then x squared times 1 will give you x squared. So you get 3y over x squared. This is the final answer. Now, one more thing I want to say about this problem before I move on is the following. Let me rewrite this problem statement again. 3x squared, whoops, not x squared, 3x to the negative 2, y to the negative 1. Now, so far I've been describing all of this stuff as a very cookie cutter, kind of like learning how to cook in the kitchen. You do one thing before the other, right? Because I want you to get those skills. I said, turn this into a proper, the fraction with a positive exponent, turn this into a fraction like this, go through the whole thing, simplify. Okay, fine. But now I'm going to take the training wheels off just a little bit here at the end of the lesson to kind of open your mind a little bit. Just like we said that we take these guys and we write them as fractions. It's not really a shortcut, but it's another way of thinking about it. What happens here in the top, you have a negative 2 power. So what you could do, but without doing any of these steps, is you could take this x to the negative 2 term and you can move them downstairs, making it a positive x squared. But then you have this negative here as well. When you have a negative in the bottom, it ends up working out that you can move him upstairs, making him positive. So if you follow that kind of rule, then what's going to happen is you're going to take this and move him upstairs, making it 3 to the positive y. And you'll take this and move him downstairs, making him x to the positive 2, which is exactly what we got in the answer. We can easily see why you can move this downstairs because that's the definition of what we've been doing. We've been taking these like this and we move them downstairs. But it also works with the bigger fraction. You just move the whole thing downstairs, making it a positive exponent. But it also works out that you can take these upstairs and make them a positive exponent. Why does it work that way? The reason it works is because if you have a negative exponent in the bottom, it's exactly the same thing as a fraction in the bottom. And anytime you're dividing by a fraction in the bottom, it always works out that you can flip them upstairs, retaining his power in the top. Okay? So there's multiple ways to do problems in algebra. The way I'm teaching you here, put this into a fraction, multiply, manipulate, get the right answer. But it's equally a good idea as we go on through problems for you to recognize patterns and see that what's going to happen as you get more experience with this is you're going to have all of this here and all of this here. This negative exponent will just simply be moved downstairs and made a positive exponent. And this negative exponent will have to be moved upstairs. And that works because of the fraction division. So bottom line is if you see negative exponents in the numerator of fractions, you can grab them, move them down below, making them positive exponents. If you see negative exponents in the bottom of fractions, you can grab them, move them upstairs, making them positive. That doesn't work because it's a shortcut. It doesn't work because it's black magic. It works because of what we've done in this problem. These negative exponents become positive and these in the bottom become positive. When you do the multiplication, the ones in the bottom get flipped over anyway. So that's why you can move things around like this. Sometimes you'll see some books teaching it like that. I'll do kind of a mixture as we go. I'll show you the long way and I'll kind of remind you, hey, you can move that there, you can move this here, making the exponents, changing them into positive exponents. So really, if you wanted to revise things, and some books actually do this, you could say, if I have a negative exponent at the top of a fraction, move it to the bottom with a positive exponent. If I see a negative exponent in the bottom of a fraction, move it to the top with a positive exponent. That's fine. You can think of it that way if you like. I'm going to end up solving the problems a couple of different ways to give you flavor of how to do this stuff. If you've had any difficulty with this lesson, watch it again, please. Go through it yourself. Make sure you understand it. You have to learn so many things here. You have to learn about negative exponents. You have to learn about zero exponents. You have to learn and remember how to manipulate fractions a lot and all the other basic rules of exponents. Putting it all together is really important because as we solve more complicated equations, we'll be using negative exponents all the time. So make sure you understand this, solve all of these problems yourself, follow me on to the next lesson, and we'll get more practice with zero and negative exponents.